What's going on, smart people? Bringing you another episode of Tensor Calculus for physics majors, and today, and really the next two videos of the series, is going to be all on the metric tensor. Today it's going to be a gentle introduction, what it is, what it's sort of used for, and then in the later videos I'll show you how it's connected to things like special relativity. Then we'll start talking about contravariant, covariant indices and how it transforms, all that good stuff. But today is the basics. It's such an integral part of tensor calculus. There is no tensor calculus without it. It's sometimes called the fundamental tensor. But before we jump into what it is, there's a distinction that needs to be made first, and that's the difference between a coordinate displacement and a distance. It's something that sounds like kind of the same thing, and in some cases they are, and in some cases they're not, which is not very helpful. So let's talk about that real quick. What I have up here is I have the displacement vector dr in three different coordinate systems: Cartesian, cylindrical, and spherical. This is something you know and love from multivariable calculus. And this displacement vector is in terms of these coordinate displacements, so our dx's and our dphi's and so on. Now, when I want to make the distinction between coordinate displacement and distance, well, in the case of dx, if we have, say, the magnitude, because we're talking about a length here, this is also a distance, right? It has units of length. But if we look at this d phi in, say, cylindrical coordinates, that's dimensionless. That doesn't have units of length, and it's this rho that gets tacked on. So it's the rho magnitude d phi that actually turns this coordinate displacement into a distance. What the metric tensor does, which we're about to get into, is it converts these coordinate displacements into distances, and we'll see sort of what this utility is in just a bit. And to make things more apparent, what I want to do is I want to deal with scalars on the left-hand side and right-hand side. I want to be dealing with components. So what I want to do is I want to call something, I want to create some variable, I'll call it like the square of the distance, and we'll call that ds squared. So ds squared is defined to be the dot product between the displacement vector and itself. So it's dr.dr. If we go ahead and carry out this calculation for these three different coordinates, we get ds squared. I'm going to drop the parentheses. This is squared, okay, it has units of distance squared, is equal to dx squared plus dy squared plus dz squared, or ds squared is equal to d rho squared. This is the fun part of just writing things out. D rho squared plus rho squared d phi squared plus dz squared. And finally, for spherical coordinates, ds squared is equal to dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Okay, hopefully I wrote that out right. I'm sure I'll put a comment in the video if I didn't, but it looks good to me. This is a bit cumbersome. It would be nice to shorten the notation a little bit, write it in a more compact manner, and in previous videos we showed how writing things in index notation can do just that. So if we adopt the convention that, x1, x2, x3, where these are not powers, they're just superscripts, they're the index saying the first component, or the first coordinate, the second coordinate. So if we say that this is, x, y, z, or if we're in cylindrical coordinates, it's rho, phi, z, and in spherical, r, theta, and phi. Can we write this in terms of just summing over these indices of the coordinates? Because that would make things a bit more pretty. Well, let's try it out. So can I say something like, I don't know, ds squared is equal to, I'll try to keep it general at first, sum over two indices of dxi, dxj. Can I say that? Well, we can write out a couple terms of this. So this would be like saying dx1 plus dx1 dx2 plus whatever, and it already failed for us. This doesn't work. This looks okay. If this is, say, in Cartesian coordinates, this is the same thing as dx squared, which is, that works so far, but then we get this cross term. That would be like saying dx times dy. That doesn't show up in this distance, so that's not helpful for us. So this didn't work. Let's drop one of the indices and just say that we're summing over the diagonals then, and see if maybe that'll work. So if I write instead, so I'm going to erase this because it didn't work, can I say that this is equal to a sum over just I of these diagonals, dxi, dxi. So let's give this a shot. In Cartesian coordinates, so this is going to be dx1 squared plus dx2 squared plus dx3 squared. And in Cartesian coordinates, that's just dx squared plus dy squared plus dz squared. Success. So that kind of works. Cool. But this may not work because we already knew that, the dx, the magnitude of dx, already had the correct units of distance. So does this work for the other ones that are a little bit funkier? Now if we do cylindrical coordinates, that's going to give us d rho squared plus d phi squared plus dz squared. That has units of distance squared. That's good. This does. That's dimensionless again. Shit. So here we're just trying to add apples to oranges. We're adding things with units of distance squared to units to no units at all. So this just gives us complete nonsense. So this was close, but it still doesn't get us what we want. What we need is, and for here, we can't just tack on, say, oh, okay, let's just multiply this by units of distance squared. Because yes, then that fixes the units here if we multiply by like rho squared. But this already had the right unit, so if we multiplied the whole thing by rho squared, now this thing has units of distance to the fourth, and that's still not right. So we need something that can fix the things that need fixing and tacking on the right units when it needs to be tacked on, and leaving the other ones alone if they're fine. And this seems a little bit familiar to when we were talking about the inertia tensor in a previous video, because what the inertia tensor did is it showed the relationship between angular velocity, something that has units of angular velocity, to angular momentum, something that doesn't have units of angular velocity. And what it does is it linearly transforms this angular velocity vector, if you recall, so I'm going to erase this now, is the inertia tensor, what it did is it established this relationship between angular momentum and angular velocity such that when the angular velocity was acted on by the inertia tensor, it transformed the angular velocity into the angular momentum. And the crazy thing about this is angular momentum doesn't have to be pointing in the same direction as the angular velocity. So we have this relationship between vectors that might not even be pointing in the same direction that are equal. What other object can give you that, can spit out a vector that's pointing in a different direction besides taking the cross product that just gives you something that's orthogonal? So this is really powerful, not to mention that sometimes they do point in the same direction. So the inertia tensor knows to rotate things when things need to be rotated and how to leave things alone when everything is fine. And this is kind of something that we need here. We need something that tacks on units of distance when units of distance need to be tacked on and leaves things alone when it doesn't. The object that does this for us is called the metric tensor. And if we follow the same logic of writing left-hand side equal to right-hand side in terms of our tensor like we did with the inertia tensor, we can write ds squared is equal to gij, where gij is the ijth component of the metric tensor, times dxi dxj, where I'm adopting the convention, the Einstein summation convention, that repeated indices are summed over. First thought that you might have is, Andrew, having both indices gave us a much more wrong answer before. Why would we go back to using 2 instead of 1? Well, the reason that we want only these diagonal terms of dx squared, not dx dy, is because we're working in an orthogonal system, right? So for different types of coordinate systems, it's fair to think that those cross terms could exist. So the metric tensor absorbs that kind of generality that we may need in the future, but it'll eliminate those cross terms if we don't need them. So this just gives us the generality to handle even more robust coordinate systems. So if we were to write this out component by component, since we have an orthogonal system, you can represent this metric tensor as a square matrix, and for an orthogonal system that means that those off-diagonal components are going to be 0. So we can say that this is equal to g11 dx1 dx1 plus g22 dx2 dx2 plus g33 dx3 dx3. You can write out all of the other terms as well. There's nothing stopping you from doing that. All that I'm getting at is that all of the other terms are just 0. And the reason for this, if we can write out the first, let's do the metric tensor for Cartesian coordinates, the simplest one. Well, this is the one that we need nothing changed, so we would say that the matrix representation Gij in Cartesian coordinates is equal to just the Kronecker delta. So if we go ahead and write this out, so for example, for those of you who might still not be used to the labeling in matrix notation, this would be like G11. This would be G12. So those off-diagonal terms are going to be 0. Only the ones for I equal to j are non-zero. So if we go ahead and substitute this stuff in here in Cartesian coordinates, we get, well, G11 is 1, dx1 is just dx. So we get dx squared plus dy squared plus dz squared. Perfect. It worked for the case where we didn't even need it in the first place. That's a good start. Let's do something a little bit more involved. Let's do the one for, say, cylindrical coordinates. So the metric tensor in cylindrical coordinates is going to look a little bit different. The metric should always look different if you're going into a different coordinate system because it is a tensor, so if you change coordinates, it follows a certain prescription on how its components will transform. So in cylindrical coordinates, the metric tensor looks like this. 1, 0, 0, 0, rho, squared, 0, 0, 0, 1. Okay? And if we go ahead and multiply out our metric tensor here, we get that ds squared in cylindrical coordinates is equal to G11, which is 1, and dx1, I probably shouldn't have erased this. So let me go ahead and write, so for x1, x2, x3, this corresponds to rho, phi, and z in cylindrical coordinates. Okay? So dx1 squared is just going to give me a d rho squared. So we get d rho squared. And then we've got dx2 squared times rho squared, so we get a plus rho squared times whatever dx2 is, which is going to be a d phi squared, plus g33, which is going to be a 1, times d3 squared. So that's going to be dz squared. Awesome. So it's working out. Everything looks good. And for those of you who are curious about what it would look like in spherical coordinates, that's what we're about to get into, because here I'm just telling you what the metric is. That's kind of, and the only reason we can do that here is because we already kind of know what the answer is, right? We know that it should be these because we know what these distance squared should be from vector calculus. But how do we calculate the components of the metric tensor if we don't already know what the answer is? That's what I'm about to show you right now. Because sure, we could just look at what the answer should be and say, well, I guess the 1, 1 component should be a 1, the second diagonal term should be an r squared, and then the third term should be an r squared sine theta. But let's pretend that we don't know that and see how do we calculate the components of the metric to begin with. So I'm going to erase all of this, and I'm going to plop this answer right up there, and then we're going to see if that's what we get at the end. So now I've just written the answer that we should get at the end. I've also thought ahead and written out spherical coordinates for us. The way that we calculate the components of the metric tensor is by taking the dot product of the basis vectors in that coordinate system. So in spherical coordinates, let's actually go ahead and calculate what those are too, because we don't want them normalized for this. So we know that the position vector r is equal to x hat plus y hat plus z hat. So if we're doing this in spherical coordinates, this is equal to r sine theta cosine phi x hat plus r sine theta sine phi y hat plus r cosine theta z hat. Great. The way that we calculate what the basis vectors are is we take the derivative of the position vector with respect to that coordinate. So for example, if we want to calculate what is E sub r equal to, it's going to be the derivative of the position vector with respect to r. So this is equal to dr vector dr, which is just going to, we're subtracting an r from all of these because it's just eliminating that power. So it's sine theta cosine phi x hat plus sine theta sine phi y hat plus cosine theta z hat. Nice. Now let's do the same for theta and phi. E sub theta is equal to, now we'll just do dr d theta, which is equal to r cosine theta cosine phi x hat plus r cosine theta sine phi y hat minus r sine theta z hat. And lastly, e sub phi dr over d phi, which is equal to minus r sine theta sine phi x hat plus r sine theta cosine phi y hat minus, and that's 0. Great. So now we have what our basis vectors are to calculate the metric. So if I want to say, I want to calculate what is Gij equal to, what it is it's equal to EI dot EJ. Okay, so let's go ahead and take the dot products between these basis vectors. Now, since we're working in an orthonormal coordinate system, well, in this case we haven't normalized them, so we're an orthogonal system, we don't actually have to evaluate these off-diagonal components for I not equal to j, because they will be 0 because our system is orthogonal. So let's only evaluate EI dot EI. That is just going to give us a diagonal matrix. So right now I'm saying that I'm not calculating all 9 components because 6 of them are going to be 0. And if you really want to prove it for yourself, just go through the motion of taking the dot products of the off diagonals if you would like to. So if we go ahead and take the dot product of ER dot ER, that's GRR, is equal to ER dot ER, which is equal to, so that's going to give me a sine squared theta cosine squared phi plus sine squared theta cosine, nope, sine squared phi, there we go, and a cosine squared theta. Great. So if we look at that, we can factor out a sine squared theta, which is just giving us a cosine squared phi plus sine squared phi. That's just 1. And then when we factor it out, then we've got sine squared theta plus cosine squared theta, so that's equal to 1. So we've already calculated one component of this metric. Let's go ahead and write that up here. I don't need this anymore. So again, Gij is equal to EI dot EJ. And we have GRR is equal to 1 based off of this dot product. Now let's go ahead and do it for this one. So G theta theta is equal to, let's do this dot product, so that's going to give me an r squared cosine squared theta cosine squared phi plus r squared cosine squared theta sine squared phi minus r squared sine squared theta. Okay, let's take a look at this. So we've got a cosine squared theta here, a cosine squared theta here that we can factor out, as well as an r squared. And that's going to give us a cosine squared phi plus sine squared phi, which is just 1. And then we also get the sum of squares. So let's just write that out. So this is going to equal r squared. And we factored out the cosine squared theta. And then these cosine squared phi, sine squared phi go to 1. And then we get a minus r squared sine squared theta. And the minus should actually be a plus because we're doing minus times minus, which is plus. So that was my mistake. This is a plus. Plus r squared sine squared theta. Again, factor out r squared. That goes to 1, which gives us r squared. So we get that g theta theta is equal to r squared. Making progress. Last one, I'm going to erase this work. That way I can do this one real quick. So we get that. Oh my god. No. Sorry, my cat was going to knock over my cup of water. E phi phi. So G phi phi is equal to minus r squared times minus r squared. So we get an r squared sine squared theta sine squared phi plus r squared sine squared theta cosine squared phi. We've got a common factor of sine squared theta and a r squared, so that's r squared sine squared theta. And then we've just got sine squared plus cosine squared, which is 1. So that tells us that g phi is equal to r squared sine squared theta. Cool, now let's collect all of this and put it in a matrix. So I'm always running out of real estate on this whiteboard and have to erase. I know a lot of people don't like when you erase, but I gotta do what I gotta do. So that tells us that in spherical coordinates, the matrix representation of Gij is equal to 1, 0, 0. And then we've got theta came next because we had r theta phi. So 0 r squared 0 and 0 0 r squared sine squared theta. And if we go ahead and multiply this out with our displacement vectors, so if we do ds squared is equal to gij dxi dxj, well, again, all the off-diagonal terms are 0, so we only have to sum the ones for I equal to j. That gives us g11 is 1, and then this is r, so it's dr squared, plus g22, which is r squared, and then the second coordinate is theta, so it's going to be d theta squared. And then the last one is g33, which is r squared sine squared theta, times d phi squared. There we have it. We were able to get the right answer, the ds squared, by explicitly calculating the components of the metric tensor instead of just pattern matching because we already knew what the answer was. In future videos, soon videos actually, we're going to be going much more in depth with this tensor. It doesn't stop here, and it's going to play a huge role throughout the rest of this series. Then we'll start taking derivatives of tensors and talking about covariant and contravariant indices. What does it mean to actually raise the indices of this tensor? But I plan on making these videos every other week. Let me know in the comment section if you're excited for the more consistent tensor calculus videos. Also, let me know in the comment section if I should do another one next week, or if you want a buffer in some other heavier math and physics video that's not necessarily tensor related. So let me know in the comments, and I'll see you guys there. Tensor Boy out.